Hello everyone, Math Cat here. Oh no, your friend is falling out of the sky again. Um, so the distance he's falling from can be drawn as h, and the distance, how far you are away from your friend, can be marked as a distance x. So, he's falling at a rate of 27.3 meters per second squared, and you're trying to run at him to catch him at a rate of 4 meters per second squared. So, do you notice the language I've kind of used? Rate? A rate is essentially just a derivative with respect to time. So if something is changing, like the height, he's falling at a rate of 27.3 meters per second squared. It's just how fast the height is changing in respect to time. And over here, it's how fast the distance or the horizontal distance is changing in respect to time. So this is the vertical distance. This is the horizontal distance. So we can denote that as the change in vertical height, how fast that changes in respect to time. So if h is the height, the vertical component between you and your friend, this would be the rate of which the vertical distance is changing in respect to time. And same thing here. Can you create a rate similar to this for horizontal distance? I'll give you a moment. Well, hopefully you tried that. It would just be dx dt, the change in horizontal distance, x, in respect to time. So another example would be if water is leaking out of the cone, the volume is changing, right? So you would write the rate as dv dt, where v is the volume, and in this form, it says that the volume is changing, how fast the volume is changing in respect to time. So a rate is a derivative with respect to time. With respect to time. Now let's move on to very useful tools that you will use when you're trying to solve related rate problems. So, hopefully you're familiar with the chain rule. But if not, let's do a quick review of the chain rule and implicit differentiation. So let's start with implicit differentiation. Let's say you just take the derivative of x to the third. Using the power rule, we know that this is 3x squared, right? There's no extra term. And that's what they want you to think. There is an implicit term. You multiply this by dx over in respect to x. And this actually just cancels out to 1. So that's why it's implicit. We don't write that. It's unnecessary. Now, let's say you take a derivative of the same thing, but it's in respect to a different variable. dy x cubed. Well, that would be just the power rule, the same thing here. 3x squared times dx dy. Now this cannot cancel to 1. Why does this appear? Because of the chain rule. If you apply, let's say, in respect to y of, actually no, not respect to y, let's do t, of f of x, this would be the derivative of the outside multiplied by the derivative of the inside. So you can kind of see that this form is taking shape in these equations. And the same thing applies for the product rule and the quotient rule. So just as a quick reminder, let's say you have d dt of a product of u and v. This would be, do you remember the product rule? That would be f prime times g plus g prime times f. So let's define f. F can be u, f prime, that would be du in respect to time. And then g can be v, and g prime would be dv in respect to time, because we're differentiating using respect to time. Like if this was a y, then this would be a y, this would be a y. And then we would just write it out. Identify du dt times g plus g prime times u. And this would be your answer. Now, let's move on to some problems involving related rates. So, before we even begin with solving the problem, we need to list out everything we know, and also drawing a picture may help. So, let's say we have a ladder that leans against a wall. Okay, well, this ladder is 10 feet tall, so let's immediately write that out. We can label that as a height h, and I got that before I even continued reading the whole problem. So a 10-foot ladder leans on a vertical wall. The base slides away. Let's write 10 feet. The base slides away at a rate of 2 feet per second. So, how fast is the top sliding down when the base is 6 feet away from the wall? So, if the base is 6 feet away from the wall, let's label that x. We know that x is 6 feet, and the base slides away at 2 feet per second. That's very important. Can you try and find a rate in like the derivative notation to respect to time? I'll give you a moment. Hopefully you tried that out. That would be dx dt is equal to 2 feet per second. So the x is changing in respect to time at 2 feet per second. How fast is the top sliding down when the base is 6 feet away from the wall? Well, for related rates, we want to try and find an equation that fully encaptures our situation. So, if you can see here, try and find a shape that we can use and an equation for that shape. Hopefully you tried that. I can see here that it kind of creates a triangle situation. And if we just draw out that triangle, that would be right next to the drawing. this would be 6 feet, and this would be 10 feet. And then there's this unknown here. Let's label that y. So we can use the Pythagorean theorem to create kind of an equation that will help us find the rate of change of how fast is the top sliding down. So you want to know when this, like how fast it slides down. That would be, we're trying to find the rate of the y, like the rate of the vertical height, and how it changes in respect to time, right? So we would want to, again, the Pythagorean theorem, we know that it's a squared plus b squared is equal to c squared. Let's change it a bit due to our situation. X squared plus y squared, and that is equal to the hypotenuse, which would be this squared, so that would be 100. Now, I want to emphasize that before we plug in any numbers, actually I think it's good practice if we just write it as h squared. Before we plug in any numbers, we need to make sure we finish all the algebraic steps, like solving for the derivative in respect to time. So do not plug anything in until the end. It often makes all the steps a lot easier. And if you want to plug things in before the end, do not plug anything in before differentiation. So we have this system here. Let's find the derivative in respect to time. So let's apply the derivative in respect to time across the whole system. Plus y squared, and that is equal to the derivative in respect to time of h squared. So let's apply the derivative in respect to t to all these terms. So that would be 2x times dx dt plus 2y times dy dt over 2h times dh dt. And I want you to notice something. What can we do about this side of the equation? dh dt, that is just that's saying that the rate of the ladder length changes in respect to time. But if we look at our situation, does the hypotenuse of the ladder change? Does the rate of, or does this length ever change? Is there a rate that can be applied to that? The length of the ladder, I don't think it's possible for it to change for our situation. So the rate of which the height of the ladder is changing at is 0. So this can be immediately crossed out to 0. Now we have this side of the equation, 2x times dx dt, and so on. What we're trying to find is how fast is the top sliding down when the base is 6 feet away from the wall. That would be, we're trying to find dy dt, how fast the top part is changing in respect to time. So how fast y changes in respect to time. So we can rewrite this equation. 2x times dx dt. This is equal to negative 2y times dy dt. And one thing important to note is that we need to include direction in our rates. So going up here, let's define that the positive x direction is to the right and the positive y direction is up. So we know that dy dt must be negative at the end. So now we can distribute the negative and let's try and get dy dt by itself. And notice, because we have all these other variables, it's just as simple as solving for this variable. So then we get 2x dx dt over, say, negative 2y. Okay, I lied earlier, but we don't have y. So let's find that using the Pythagorean theorem. So we have 6 squared plus y squared, that is equal to 10 squared. 10 squared minus 6 squared is equal to y squared. So to find y, we need to take the root. If you're wondering what I'm doing here, this is just the Pythagorean theorem. So 100 minus 36, what is that? 64, and that means the square root of 64 is equal to y. Y is equal to 8. Now we have everything. So what is our x again? Our x is 6 feet, and the change in x in respect to time is 2 feet per second. So rewriting this, plugging in everything after we're finished, this would be 2 times 6 times dx dt, which was 2, I believe. And this is over negative 2y, and y was 8. And this is equal to the change in height in respect to time. Calculating this, 2 times 2 times 6, that would be 24 over negative 16. And this roughly simplifies to negative 1.5 feet per second. And that would be the change in height in respect to time, which is what the question originally asks us. Right? How fast is the top sliding down when the base is 6 feet away from the wall? So at 6 feet, that is when x is 6, and it's sliding at a rate of 2 feet per second, and the height is 8 at that specific time. This is our final answer, and we know it's correct because it's negative and it's sliding down, and we defined negative as going down. We can make sure that our answer is correct by performing dimensional analysis. So it's just plugging in the units here to make sure they cancel out correctly. So 2x, that would be a unit of feet times feet per second. Feet per second, with that feet per second squared. No. Over 2y, which was a feet as well. These cancel, and this returns our answer of dy dt feet per second. And we know that it's correct. Now, let's try another problem. A tank with the vertex down has height 10. So let's first draw the tank. With the vertex down, and it has a height. Let's denote the height as h. And a radius, okay, a radius of 5 feet. Water drains at 3 feet cubed per minute. How fast is the water level falling when h is equal to 6 feet? So we have our smaller height. So let's make this big height. And let's make this, actually let's name it K. Big K. And this can be little k. It's at 6 feet. So that's the height of the water. And it's leaking out at a rate of 3 feet cubed per minute. So this would be the change in volume in respect to time. So writing out all of our variables, our radius would be 5 feet. Our height of the tank, this is big K, would be 10 feet. And little k would be 6 feet. What if I use another unit measurement to make it easier? Length, or L. And we have the change in volume. Let's make it white. The change in volume in respect to time is 3 feet cubed per minute. Now see if you can solve this problem by yourself. I'll give you the formula for a cone and see if you can solve it by yourself. Here's the equation for the volume of a cone, where this is the radius and this is the height of the cone. Given this, we can actually try out with solving. So we need to find what the rate is, the rate of change of the height of the water when the height is 6. So knowing that, we can't immediately just start by using these variables, because if we started and plugged that in, it would assume that our water height is starting from up here, and the rate at which the water is falling would be different, or it wouldn't work. And then, so what we need to do is we need to find the height and radius of the water when the height is 6 feet. We need to utilize something called similar triangles. So if we create a triangle up here, we can see another triangle where the water height is at. Let me draw it separately from the diagram to make it clear. This is where the water height is at. Notice how these triangles are similar if I draw them separate. This triangle is essentially a scaled up version, maybe by a factor of 2, 3, I'm not sure, but it's just scaled by a factor of this triangle. If we know the height and radius, of one of the triangles, we can find the radius and height of another triangle because it's based off of a ratio. Like, let's say this triangle has a height of 2 and a radius of 4. And let's say this bigger triangle just doubled in size. So that would be 8 and 4. If we take the ratio, radius to height, height to radius, because they depend on each other, we can take the ratio 8 over 4, which would be the radius over height, is equal to the ratio of the radius over height here. This is equivalent, and also other way around works. Let's say you want to take the ratio of the height to radius instead. That would be 2, 4, height to radius, 4, 8, and these are equivalent. So that's just a recap of similar triangles, and we need to use it to solve for the radius at this specific height. We know that the ratio of, let's just do radius to height, the ratio of that is equal to 5 over 10. And this is equal to the ratio from the radius to the height is a half. So that means that the radius is approximately half of the height. So we can rewrite that as half of the height is equal to the radius. And then we can plug that in to this equation to get the formula in terms of just height. And we get rid of a variable, which helps us out a lot. So we can rewrite this as v is 1/3 times pi, and the radius is changed. It's half of the height, so that'd be h over 2 squared times height. So for this specific situation, this formula remains, or this formula is consistent. Now, if we simplify this, this would be v is equal to 1/3 pi over h squared over 4 times h, and this is equal to 1/3 pi, or let's do 1/12 times h cubed. And then now, this is the formula you want to find the derivative of in respect to time. Now, applying the time derivative, dv dt is equal to 1. Let's take the constants out first, and then now the derivative in respect to time of the height cubed. We can take out these constants because of the power rule. We can do that, and then taking the derivative of this would equal 1/12 pi times 3h squared times the change in height in respect to time. Now if we look at all of our variables, we have the height, the radius. Let's define that little radius. This can be p. Little radius would be 3 feet. We have everything. This is our formula that we want to use, so let's isolate the change in height in respect to time. That would be 12 over pi times dv dt, and that is equal to, I forgot to do something, times 1 over 3h. There we go. Now that is equal to dh dt, and this is squared. So canceling this out, canceling this 3 and 12, we get 4 over pi times the change in volume in respect to time, and that is equal to the change in height in respect to time. And I forgot to include times 1 over h squared. So at that specific height, at this height, it is a height of L, and L is 6 feet. L is 6 feet. So we can plug that in. 4 pi times 1 over 6 squared times the change in volume in respect to time, which would be 3 feet cubed per minute. And that is equal to dh dt. Simplifying this down, it's just a matter if you can get the algebra correct. 12 over 36 times 1 over pi, which is equal to 1/3. Something I forgot to include earlier, it would be changing. The volume would be negative because it's losing volume. That's important to note. So then our change in volume would be negative. So then our answer would be negative 1/3 over pi is equal to the change in height in respect to time. And this would be our final answer, but make sure to include units. Feet cubed. Oh no, just feet per second. Let's rearrange this. Our final answer would be 1 over 3 pi negative feet per second. And this would be the change in height in respect to time. And that is the cone tank problem. Okay, now we have a trough that's leaking water. Same principles as the cone problem, but just different shape. So, drawing this out. Oh, see a different color. A trough. This is a trough. I hope you can trust me on that. And it is 4 feet wide at the top. So we can denote that as a width W, and it is 3 feet deep. So that means it has a height of h. Water fills in at a rate of 2 feet cubed per minute. So we immediately know that the change in volume is positive 3 feet cubed per minute. Okay, I made an error. This is supposed to be 2. I read the problem wrong. 2 feet cubed per minute. And we know that the water level is at 1. Let's do blue water. So the height of the little water. Let's do P, the height of the water is 1 feet. Now I'm defining all of our variables. The height is 3 feet and the width is 4 feet. Can you find an equation that helps capture the shape of this water trough or this situation? It would be, what is the volume for a triangular prism? It's just V is equal to 1/2 times the width times the height times the length. Oh, I forgot to say that this trough has a length of L, which is 10 feet. Okay, now we have our equation and we're trying to find the change in height. So is there a relationship where we can get rid of W, where we can get it in terms of the height? Well, we can use similar triangles again. So if we kind of zoom, make a bigger picture, this would be the trough at this specific view. There's a triangle that we can make and it's filled with water. We know the width is W, but for this triangle, for this section, it would be the width over 2 and then the height of H. So the width, let's try to find the height in terms of the width. We know that the width, half of the width would be 2 over 3. The height is equal to, and because we know the ratio now, we can do the width over 2 over H. This is our relationship. Now to get it in terms of the height, flip the variable. 3/2 is equal to H over 2, and just multiply this to this side, and we get for the width, oh sorry, I was blocking it, we'll get 2/3 times, 3/2 times width over 2 is equal to H. So this would be 3/4 of the width is equal to height. Now that we have this relationship, because we set up this ratio, I just plugged this in and then set it equal, and we can solve for a variable. Now we have the width in terms of the height. This would be 3/4 of the width is equal to the height. That would be V is equal to 1/2 let's isolate, let's move this to the other side. So the width would be 4/3. We want to get rid of this width to get it in respect to the height. How fast is the water level rising? That relates to the height. H 4/3 times 4/3 times the height times the length. Now we have our equation in terms of height. because L doesn't change, it's not a variable anymore, that could just turn into 10. Simplifying this to get the volume in terms of height, that would be 40 6 times h squared. Now, taking both sides in respect to time, the change in volume in respect to time is equal to 46. This is a constant, we don't care about that. In respect to time of a squared, the derivative in respect to time, which is equal to times, let's keep this purple actually, so you can keep track. It'd be 2h times the change in height in respect to time. Now, this is what we want, okay? We can just kind of like delete this, and that would be our equation. Now, we just need to do some algebra. 640 times the change in volume in respect to time, all divided by the height at that specific time, is equal to the change in height in respect to time. And that can be simplified to 1240 over 2 divided by 1, which is equal to 12 over 80, 640, 320 feet per minute. And this would be the change in height in respect to time. Nice, that is the trough problem. Okay, you have a 20 feet street light. 20 feet street light, very bright. And it casts a shadow of a 5 feet person walking away at 4 feet per second. He is 5 feet. Let's label that a height of D. Actually, no, height of Y. And this can be a height of H. And it's casting a shadow, so I would assume the shadow would be somewhere on the ground. Let's make the shadow green. This line just representing the shadow. The length of the shadow can be S. How fast is the shadow length increasing? So we need to find the length of the shadow, which is the rate of change of the length of shadow in respect to time. And let's focus on finding this first. So we can label the distance between the two as x. And notice, do you see a triangle and a similar triangle case? This triangle is just a smaller version of this triangle. Nice. We can create the relationship that, let's say, we know the height is 20 feet and the height of the person is equal to 5 feet. So we can create a relationship, a ratio through similar triangles. That would be, let's do the height in respect to the length. So the height would be 20 feet. Let's start with the big triangle, 20 feet. And then the length, x plus s. Oops. This is equal to the ratio of the height to length of the smaller triangle, and we know he's 5 feet, So 5 over s, which is, we don't know. So now we have this formula here to get the denominator to the numerator. We can take the reciprocal, which is s plus x over 20 is equal to s over 5, right? Now, how fast is the shadow's length increasing? That means we only care about s. So let's get s in terms of x. Expanding this, that would be s over 20 plus x over 20. And this is equal to s over 5. And we can just move this to the other side. So we get x over 20 is equal to the length of the shadow over the height of the person minus the length of the shadow over 20, or the height of the lamppost. And simplifying this out, we should get x over 20 of s, 15s over 100. And now, to isolate s, we can do 5 times x divided by 15 is equal to s. So that is roughly 1/3 of x is equal to the length of the shadow. Now we can finally take the time derivative. The time derivative, so the change in x in respect to time times 1/3 is equal to the derivative of the length of the shadow is respect to time. I should make this red. Now, originally we were trying to solve for that, and we have it in a combination of things we know. dx dt, that would be what? It's moving, the person is moving away at a rate of 4 feet per second, right? So that would mean that he is changing in x in respect to time at a rate of 4 feet per second. So that'd be 4 feet per second times 1/3 is equal to 4/3 feet per second. And this would be equal to the rate at which the length of the shadow is increasing. That answers the first part of the problem. But what is the second part of the problem? How fast is the tip of the shadow moving? Well, the tip of the shadow can be modeled after x plus s, because we want this point here, right? So x plus s and we just need to take the time derivative of that, which is equal to dx dt plus ds dt. You just add up the rates together. 4/3 feet per second plus 4 feet per second. That would be equal to 16.3 feet per second. That would be, let me box both of my answers. So that is the rate at which this entire length is increasing, not just the length of the shadow or the distance the sky is making, is the length of the entire, or the tip of the shadow. That is the street lamp problem. Now, at noon, a car is 60 miles north. So let's create our point. Oh, it's a box. He is 60 miles up north. The car can be green car A. It is 60 miles north and traveling south at 30 miles per hour. Let's label our axes. This can be blue, Y, and it's traveling east. Car B is at the intersection and is traveling east 40 miles per hour. How fast is the distance changing at 1 p.m.? So, this is our snapshot at 12 at noon, 12 p.m. But after 1 hour, they are at different spots, right? So now, maybe car B is here. And car A is now at a distance, let's say distance y2. This is y1. This is at 1 p.m. So y1 is equal to 60 miles north in the x direction, or y direction, and car B is at 0. But for now, yeah, x1 is equal 0. And this can be x2. And at 1 p.m., it travels 30 miles per hour because it takes an hour. It travels 30 miles per hour. So now, y2 is equal to 30 miles away from the origin, right? And x2 is now, because it's traveling east at 40 miles per hour, after 1 hour, it travels 40 miles to the right. So that is 40 miles. And now, the change in height with respect to time, we know that based off of traveling south 30 miles per hour. So dy in respect to time, let's make that blue, that is equal to 30 miles per hour, but it's negative because let's define right positive, up positive, and down negative, left negative. And dx dt is equal to 40 miles per hour in the positive direction. Is there a shape that we can use to help us map out the situation? Yes, we can use a triangle. So the distance would be the hypotenuse between the two cars at 1 p.m. So y2 is 30. We use the second situation because we only care about how fast is the distance changing at 1 p.m. So these values, we can actually just get rid of them. They don't factor into our final calculation. And then x2 would be 40 miles away, and the hypotenuse would be the distance. Let's name that distance d. We can use the Pythagorean theorem now. D squared is equal to, actually just d is equal to the square root of 30 squared plus 40 squared, and that is equal to 250, I believe. No, I lied, 50. So d is 50. And now let's write out our equation. We have x squared plus y squared is equal to d squared. And what we can do is now we can take the time derivative, because we know x and y, and we know the change in respect to anything, and y and x do not depend on each other. So we can just simply take the time derivative on both sides. D dt times d dt. So that would be 2x times dx dt plus 2y times dy dt, and it is equal to 2d dd dt. And we want to find again how fast is the distance changing, and we have it here. This is how fast the distance is changing, and we know all of these. So at 1 p.m. x distance is 40. 40 times 2 is 80 times the change, which is 40 miles per hour in the positive direction, plus 2y. y is 30. 30 times 2 is 60 times the change in y in respect to time. Because the car is going down, that is a negative change in y, so negative 30. And that is equal to, let's isolate the change in distance. So we would divide this all by 2d. And d, the distance we found earlier at 1 p.m. is 50. So that would be 2 times 50 is 100. This would result in the change in distance in respect to time. Calculating this, we get 3200 plus negative what? 14? Oh no, negative 1800 divided by 100, and that is equal to 14. And the change in distance in respect to time is miles per hour. This is your final answer. You made it to the end. If you're watching this before the AP Calc test, good luck. Hello everyone. Thank you guys so much for watching. I really appreciate everyone who watches my videos through and through, and hopefully those who watch it fully can give me some feedback to better improve my teaching, because I am not, I wouldn't say I'm a teacher, but yeah, get all this wonderful fan art, and I I will be looking into posting more calculus later. I wanted to post this before the calculus tests on Monday. AP Calc test? Yep. But I will be looking to delve more into calculus as time goes on, and I've been really busy with like scholarship applications and filling out a bunch of stuff. It's taking up a lot of my time. But hopefully this video helped, and I just know that I will eventually post math videos covering every like section, like the organic chemistry tutor. It's a big inspiration to me. And yeah, thank you so much for watching.